everyone, and welcome back. A big shout out to our listeners. Credits Gustavo Gomez as both the producer
Oh, wow.
and the director.
It's funny how often we think about it, just popping back to yesterday. Or even jumping ahead.
Oh, absolutely. It's everywhere in fiction, isn't it?
Yeah.
H.G. Wells, Interstellar.
Exactly. And you can't help but wonder, is that just great storytelling? Or is there like a tiny sliver of science fact hiding in there?
Well, that's precisely the question, isn't it? Where does the fiction end and the potential science begin? And for you listening, this isn't just about being curious.
No, it feels more like a quest almost.
Yeah, a personal quest to figure out if this whole time travel thing actually holds up against what we know about the universe.
And we've got this really interesting white paper to guide us today. The impossibility of time travel and the nature of the multiverse.
Right, by Gustavo Gomez, with some AI assistance noted too. It really tries to dig into the scientific plausibility, pulling from relativity, quantum mechanics.
Yeah, it mentions Brian Greene, touches on cosmology. It's not a light read.
Definitely not.
Yeah.
So our mission today for this deep dive is pretty clear.
We want to unpack the arguments against going backward in time that the paper lays out.
And explore its perspective on the multiverse too. Give you a really solid, scientifically grounded take on these, let's face it, pretty mind-bending topics.
Okay, so let's start with time itself. It feels so straightforward, right? Like tick-tock, 1 second after another.
That's our everyday experience for sure. But the paper starts right off with Einstein, and he showed it's not quite that simple.
He kind of blew up the old view, didn't he?
Completely. His theory of relativity showed time isn't this separate universal clock ticking away. It's actually interwoven with space.
Space-time, one thing.
Exactly, a unified fabric. And crucially, this fabric isn't rigid. It can stretch, it can warp.
And that warping, that leads to time dilation. That's the idea where time can actually, like, speed up or slow down.
That's it. Depending on your speed or how strong gravity is nearby, the paper mentions astronauts, the classic example.
Right. They age slightly slower when they're in orbit or traveling fast.
A tiny, tiny fraction slower, but measurably so. Improves time isn't absolute. But, and this is a big better, the paper stresses, this effect is all about moving forward through time at different rates. Relativity, as we understand it now, doesn't give us a way to, throw it into reverse.
Okay, no reverse gear. Now, the paper gets into something really fundamental. Causality.
Ah, yes. Cause and effect. The bedrock of, well, everything logical.
The idea that the cause has to come before the effect, simple enough, right? But backward time travel, that just flips it on its head.
It creates massive problems. Logical contradictions, paradoxes. The paper brings up the most famous one.
The grandfather paradox.
The grandfather paradox. You go back, you prevent your own grandparents from meeting.
Then you wouldn't be born.
Exactly. So who went back in time? It collapses logically. There's no sensible answer.
Yeah, my brain hurts just thinking about it. Okay, what about wormholes? Sci-fi loves wormholes as time tunnels.
They do. And interestingly, the math of Einstein's theories does allow for theoretical structures like wormholes, these shortcuts through space-time.
So there's a chance.
Well, here's the massive catch the paper highlights. To keep a wormhole stable and traversable, especially for time travel, you'd need something called exotic matter.
Exotic matter. Sounds exotic.
You would need to have negative energy density. Basically, properties unlike anything we've ever observed or detected in the universe.
So the equations might allow it, kind of like a loophole.
But the physical ingredients needed to actually use that loophole seem to be completely missing. It's like having a blueprint for a warp drive, but no dilithium crystals,
Gotcha. Okay, so Einstein's view. Time is flexible, but forward only. What about quantum mechanics? The really small scale? Things get weird down there.
Oh, incredibly weird. And the paper definitely dives into that. It talks about superposition.
Where a particle can be in multiple places or states at once. Until you look at it, sort of?
Sort of, yeah. An electron could be spinning both clockwise and counterclockwise simultaneously, for example. Until you measure it, then it picks one.
So multiple possibilities exist at the quantum level. Does that mean time could somehow branch or reverse down there?
That's the key question the paper tackles. And its answer is pretty clear. No. Just because a particle can exist in multiple states doesn't mean the process of time can run backward.
How do they explain that?
They use a really neat analogy, actually, the water pipe analogy.
Okay.
Imagine water flowing through a pipe that splits into, say, 3 different paths. The water can explore all those paths, kind of like superposition.
Right.
But once the water has flowed through, it can't just spontaneously decide to reverse course, collect itself perfectly, and flow back to the single entry point.
Ah, I see. The flow itself is still one way.
Precisely. Even with quantum weirdness and multiple states, the actual progression of events, the unfolding of time, still seems to have this fundamental irreversible direction. Like sap in a tree, many branches, but the flow is always up from the roots.
That makes sense. Okay, so quantum mechanics doesn't offer a backdoor. What about entropy? That always comes up with the direction of time.
The second law of thermodynamics, yes, absolutely crucial. It's one of the solid laws in physics.
And it basically says things tend to get more disordered over time.
In any closed system, yes, total entropy or disorder can only increase or stay the same. It never naturally decreases on its own. This is what gives time its arrow.
My desk is proof of that law. So how does this stop time travel?
Well, think about reversing time. It wouldn't just be like rewinding a movie.
Right.
You'd have to reverse every single interaction, every molecule's movement perfectly. You'd essentially have to decrease entropy.
You'd have to unspill the milk perfectly, unbreak the egg.
Exactly. And the paper uses another analogy here, the maze analogy.
Another analogy, okay.
Imagine pouring a liquid through a super complex maze. It spreads out, goes down different paths. Now, try to reverse that flow perfectly so every single drop retraces its exact path backward.
Seems impossible because of all the mixing and randomness.
Precisely. The natural tendency is always towards more mixing, more disorder, higher entropy. Reversing time perfectly would mean undoing all that inherent randomness, forcing a massive decrease in entropy. The second law says that's overwhelmingly improbable, practically impossible for any complex system.
Wow. Okay, so thermodynamics puts up a huge roadblock. What about the really big picture? Cosmology, the universe itself.
Cosmology adds even more weight to this idea of a one-way street for time. We observe the universe expanding.
And speeding up, right, due to dark energy.
Exactly. It's been expanding since the Big Bang, and that expansion is accelerating. The paper points out the Big Bang itself was a singular event.
You can't rewind the Big Bang.
Doesn't seem like it. It was the start, the origin point. And this accelerating expansion, driven by dark energy, makes a future big crunch where the universe might collapse back in on itself look very unlikely based on what we see now.
So the universe's own evolution points forward only.
From the quantum level to thermodynamics to the cosmos as a whole, yeah, the picture seems remarkably consistent. Time moves forward.
Okay, so the case against going back seems pretty strong based on this paper, but the title also mentioned the multiverse. That feels like a whole different can of worms.
It really is. And the paper definitely ventures into that more speculative but fascinating area. It brings in ideas from string theory, mentioning physicists like Brian Greene.
String theory. That's the one with tiny vibrating strings and extra dimensions.
That's the one. The idea is that besides our familiar 3 dimensions of space and one of time, there might be other spatial dimensions, curled up very small.
And how does that lead to a multiverse?
Well, the way these extra dimensions are curled up or configured could be different in different regions of, well, whatever reality encompasses everything. Each different configuration could potentially result in a universe with slightly or even vastly different physical laws.
Like tuning a radio to different stations, each playing different music.
That's a decent analogy. Different configurations, different universes. The paper also touches on inflationary cosmology.
Inflation. That rapid expansion right after the Big Bang.
Yes, and a related idea called eternal inflation. This suggests that the process that started our Big Bang might be happening constantly, creating countless separate bubble universes, each expanding on its own.
Wow, so potentially infinite universes just bubbling up.
That's the mind-boggling picture some theories paint. Now, the white paper adds its own interesting twist to this.
Oh, what's that?
It proposes a model centered around a central core of energy.
A central core, like a source.
Sort of. They use the analogy of a boiling kettle. This core in their model is like the heat source, and it periodically releases energy in controlled bursts, creating universes.
Like bubbles forming in the kettle.
Exactly like that. Each bubble is a new universe.
And what happens to these bubble universes then?
In this model, once formed, they expand and move away from this central core and also away from each other. The paper even speculates this outward push might contribute to the accelerating expansion we observe in our own universe.
That's a really different way of thinking about cosmic expansion.
It's definitely a novel perspective presented in the paper.
Okay, so we have this potential multiverse maybe bubbling off a central core. But even if that's true, does it change anything about going backward in time within one of these universes, like ours?
And that's where the paper circles back very firmly. The answer is still no.
Why not?
For all the reasons we already discussed. The logical paradoxes, like the grandfather paradox, still apply within any given universe with cause and effect.
Right, those don't go away.
There's still no known physical mechanism, even in these multiverse scenarios, that would allow time to flow backward.
No reverse gear discovered.
And the arrow of time, driven by entropy, still points relentlessly forward within each expanding universe. The fundamental barriers remain.
So it seems like whether you look at relativity, quantum mechanics, thermodynamics, cosmology, or even these multiverse ideas,
The conclusion is consistent. Backward time travel faces seemingly insurmountable hurdles based on our current understanding of physics. It's not just one theory saying no, it's the convergence of findings across different fields.
the paper also brings up something more philosophical, doesn't it, about how we perceive time versus maybe what it really is.
It does. It touches on this potential gap between our human linear experience of time, past, present, future, flowing steadily, and the deeper, perhaps more complex reality of the cosmos,
Maybe our perception is just like a convenient illusion.
or at least a limited view. The paper hints that the fundamental nature of reality might be structured in a way where our sense of linear flow is just one aspect of a much larger, irreversible cosmic process.
And it admits we don't have all the answers, right? Like, what is this central energetic core if it exists?
Absolutely. It acknowledges the limits of science. We build models, we test theories, but some ultimate questions like the origin of everything or the precise nature of such a core might still be beyond our current grasp. That core idea is a hypothesis, a potential explanation, not established fact.
Okay, so let's try to sum this up. This deep dive into the Gomez white paper. It's really laid out a strong case against traveling back in time.
Definitely. We hit the logical paradoxes. Huge problem.
Check. Then the lack of any actual physical way to do it.
Check. No mechanism known.
And finally, the big one. Thermodynamics. Entropy. The arrow of time.
Check. That one seems fundamental. And even looking at the multiverse, whether from string theory or this central core idea,
Still doesn't provide a loophole for reversing time within a universe.
seems not. The paper argues convincingly that backward time travel remains firmly in the realm of science fiction based on current science.
And, while that might burst the bubble for some sci-fi dreams, understanding why it's likely impossible actually makes you appreciate the real universe more, I think. Its complexity, its rules.
I agree. It forces you to grapple with the nature of causality, the directionality of time itself. It's profound stuff.
So here's a final thought to leave you with. If going back is off the table, what else is there?
What do you mean?
I mean, what mysteries are still hidden in time itself? Could we explore forward time travel more? Like really forward using time dilation? Or maybe just understand this one-way flow better?
That's a great question. Perhaps the real adventure isn't changing the past, but fully exploring the consequences and possibilities of the future that lies ahead along this unidirectional path.
Yeah. Maybe the biggest mysteries are still right here in the time we actually experience and in the cosmos unfolding around us.
A lot left to discover, no doubt.
Well, thank you for joining us on this deep dive into these really complex and fascinating ideas from the white paper.
A pleasure. Lots to think about.
Definitely. Until next time, keep pondering those cosmic questions.